Hello everyone, I'm Nitendra Mohan from Technical University of Munich. Today I will talk about our work, Cloudy with a Chance of Short RTTs, Analyzing Cloud Connectivity in the Internet. This work is done in collaboration with folks from Uppsala University, Sweden and University of Helsinki, Finland. In this work, we present a comprehensive analysis of end-user connectivity toward networks of several major cloud providers across the globe. But before we jump into the details of the work, let me paint you a picture motivating the need of the study. Over the past 2 decades, cloud computing has become the core enabler for an ever-increasing growth of network services on the Internet. With its seemingly unlimited support for computational capabilities and storage and recent global growth, thanks to the significant investments from established and new operators in the market, cloud has become an invaluable resource to the operation of the Internet as we know today. However, the recent growth of interest in the next generation network applications has imposed even stricter constraints on the Internet compute fabric. Instead of unlimited compute capacity, applications of today demand lower latencies. The graph shows the approximate bandwidth and latency constraints imposed by many such next-generation network applications. Previous research has shown that the latency demands of most of these applications are driven by strict human vestibular thresholds. The most stringent threshold is known as motion to photon, which is the delay between the user input and its effect to be reflected on the display screen. It is estimated to be around 10 to 20 milliseconds and guides the operation of immersive applications such as augmented reality, virtual reality, etc. MTP is followed by perceivable latency threshold, which is around 80 to 100 milliseconds. Interactive applications such as cloud gaming need to abide by PL latencies to avoid noticeable lags in their performance. The final latency threshold is the human reaction time, which is typically less than 250 milliseconds for average human. It is the delay between the presentation of the stimulus and the associated motor response by human. Staying below the HRT threshold is pertinent for applications that have active human engagement, for example, remote surgery. While many previous works have focused on investigating the state of cloud networks, its performance and reachability, most of them do not accurately reflect the state of the real internet users around the globe. This is primarily because either the studies do not capture the expansion of the cloud in the past decades, or focuses on a few hypergiant cloud operators, or performs measurements from vantage points that do not represent the connectivity of real internet users. Furthermore, almost none of the studies investigate the impact of the wireless last mile on cloud connectivity, which has been widely reported to be the primary bottleneck in the end-to-end connection. On the other hand, many new cloud operators have entered into the competition recently. Existing hypergiants like Google, Amazon, and Microsoft are investing more into their network by deploying more data centers and are expanding their private WAN to reach new geographical regions. In this work, we provide a multifaceted analysis of cloud reachability across the globe from networks of real internet users. We conduct large-scale measurements from upwards of 115,000 probes hosted in the SpeedChecker platform. SpeedChecker probes are softwareized applications installed in end users' Android devices and are available in over 140 countries worldwide. Using the user population per ASN dataset from APNIC, we find that the probes used in our measurements reside in ASs that cover 95.6% of the internet population globally. Compared to RIPE Atlas platform, SpeedChecker boasts of almost 13 times more probes overall, with 30 to 40 times more coverage in South America, Africa, and Asia. Furthermore, all 115,000 probes used in our measurements are wireless in nature and connect to the internet either via Wi-Fi or cellular last mile. As a result, our measurement provides the most accurate representation of real internet user connectivity to cloud throughout the globe so far. We targeted 195 cloud regions from 9 major cloud providers with significant global coverage. We explicitly targeted regions which offer compute capabilities to clients. Our selection gives us a good mix of providers that have deployed their own low latency networks versus those who rely on the public internet. For our experiments, we triggered TCP pings and ICMP trace routes between probes towards data centers in the same continent at every 4-hour intervals. For continents with sparse data center deployments, for example Africa and South America, we also triggered experiments towards neighboring continents, that is Europe and North America. We employ a self-imposed rate limit to remain under the strict per-day measurement quota, and it takes us almost 2 weeks to cycle through probes in 140 countries. We perform several cycles of our measurements within our 6-month study period. Our dataset spanning several gigabytes is available for public use at cloudreachability.github.io. For detailed methodology on probe filtering and rate limiting, we encourage you to read our full paper. To start off, let's look at the state of the cloud accessibility globally. The CDF here shows the distribution of RTTs to the nearest cloud region throughout the globe. The plot also marks the desired latency threshold for correlation. Keep in mind that the result includes the latency at the wireless last mile, which has been widely regarded as the primary bottleneck in the past research. We observe that it is quite difficult for internet users to access the nearest cloud operated by any provider within the 20 millisecond end-to-end motion to photon delay. We only found China to consistently remain under this threshold due to the dense data center deployments within the country. On the other hand, countries in Europe, Oceania, and North America are able to reach the cloud within 100 milliseconds and are able to achieve perceivable latency requirements are quite consistently. The reason behind the trend becomes clear if we correlate the median latency per country to the number of data centers globally. We find that the density of data center availability severely impacts the end-to-end latency. Probes deployed closer to the data center enjoy quite low latencies, which degrades with increasing distances. For example, in South America, users in Brazil achieve latencies to in-country DCs within 50 milliseconds, but users in neighboring Argentina and Chile struggle to achieve the 100 milliseconds end-to-end. We observe similar trends in Asia near India. Due to the highly skewed deployment in Africa, especially favoring the southern part of the continent, a large percentage of the population is unable to reach the cloud even within the human reaction time threshold of 250 milliseconds. In fact, we find that the countries in mid and north of Africa can reach the clouds in Europe and North America much faster than the in-continent deployments. We make several additional analyses on this front and also compare our results to measurements of our RIPE Atlas platform, which you can find in our paper. Let's now turn our attention to the user-side bottlenecks in cloud connectivity. While cloud providers can improve the state of the connectivity to the private networks by deploying data centers in previously under-provisioned regions and setting up peering agreements with serving ISPs globally, they have little influence over the wireless last mile. Almost all of the next-generation applications intend to operate over different wireless mediums such as cellular, Wi-Fi, etc. Previous studies have shown that the wireless can be the primary bottleneck for a user due to frequent packet drops and invariable delays. To assess this further, we analyze our traceroute measurements and extract the latency at the last mile and in the wired backhaul. We first identify and categorize probes in our dataset based on the last mile access technology used. Probes that connect to the ISP AS via private hop is most likely going to be Wi-Fi connected, whereas those that are connected directly to the ISP are likely to be cellular devices. For Wi-Fi based probes, we also extract the latency of the wired part of the connection connecting the router and the ISP network, as shown in the figure. The plot shows the percentage share of the last mile latency to end-to-end latency towards the cloud in each continent and also compares the same value extracted from measurements over RIPE Atlas. Keep in mind that RIPE Atlas probes are largely wired in nature. Firstly, we find that the percentage share of the last mile is similar across both access technologies, almost globally, highlighting similar performance bottlenecks at the last mile. Please note here that if we only compare the latency due to the wireless parts of both connections, Wi-Fi outperforms cellular by a very large margin. Secondly, we observe that the percentage latency share of the last mile is much higher in Europe, North America, and Oceania, and accounts for almost half of the total end-to-end latency. We attribute this to the significantly lower latencies in wired backhaul within these regions, thanks to the dense cloud deployments and investments in the private WANs. To understand the overheads of last mile better, we also plot the latency at the last mile in absolute numbers. We find that the nature of access technology has little influence on the overall cloud access latency across the globe. End users experience similar latencies on both Wi-Fi and cellular, which ranges between 20 to 30 milliseconds. Interestingly, the latency at the last mile itself exceeds the motion to photon latency of 20 milliseconds, which also explains why the threshold remains largely unachievable in our global cloud results that we showed earlier. Note that even bringing the cloud compute capability closer to the users by the mean of edge computing is not going to help much, since the last mile will continue to make the MTP threshold unachievable. The result motivates the need for significant investments in improving the wireless access technologies if we need to support the strictest of the next generation applications in the near future. This was just a sneak peek of the takeaways we make in this work. We perform several other analyses that paints the most comprehensive picture of cloud reachability for internet users so far. Specifically, we shed light on the state of the cloud accessibility in different parts of the globe and highlight the performance differences between different cloud operators. We also compare our results of our speed checker to RIPE Atlas and showcase the inherent biases due to the makeup of different measurement platforms on drawn inferences. We isolate the impact of the wireless last mile on cloud latency and analyze how the coveted hop impacts the overall performance in different regions and countries across the globe. We also analyze the reach of the WAN deployment of cloud providers that help them achieve low latencies in the network backhaul. Finally, we identify different peering interconnections that exist between the cloud providers and the serving ISPs in different continents. Specifically, we investigate if the enhancement in the network backbone by providing clients private transit and shortening their paths through private WANs can allow the cloud providers to achieve consistent performances without the need for deploying data centers in newer locations. We also make our dataset and helper scripts available for public use. To learn more about this work and other related studies assessing cloud reachability from different perspectives, please visit cloudreachability.github.io. Thank you for listening to this talk.